In this video, I'll show you how I made an auto-aiming enemy using nothing but basic trigonometry, and how you can too. So, without further ado, let's get into it. So yesterday, the video was really laggy, so I'm just going to redo my yesterday's video. Now, today we're going to be talking about how to implement a projectile system into your game. And what I mean by that is we're going to be talking about auto-aiming enemies, and the ones that shoot at other entities and damage them. Yeah, we're going to be talking about how to implement that along with the math that you need. So if you're just not interested in how I get the formula for calculating the angle to fire, just skip right on ahead. But I'll just be talking about how we actually get a huge and crazy formula. But anyway, the first thing we do, is just look at the Wikipedia page. Wikipedia has a lot of information. Now, the first thing we need to know about projectiles is actually how to calculate its position. Otherwise, there wouldn't be a projectile. So, under this displacement category, we'll have at any time t, the projectile's horizontal and vertical displacement are x equals vt cosine theta and y equals vt sine theta minus half gt squared. Now, if you know some basic trigonometry, you'll actually find that this actually makes a lot of sense. Now, that's the wrong tab. If we go back to this drawing board, we'll see that for this angle theta, we can actually calculate the x position of the trajectory with v cosine of theta. Remember, cosine theta is actually the x position, while sine theta is the y position, right? Well, we have this extra v over here, and what this v means, what this stands for, is velocity. Because, projectiles always move like different speeds. You have some that move slowly, some move fastly, and this v just tells us how fast it goes. Now, we also have, obviously, we have t. T stands for the time, and as time goes on, obviously, the position should change, right? So that's how, that's basically the basic idea of how this formula basically came to be. Now, this is really important, so I'm just going to write it down on the drawing board real quick. I'm going to write x is going to be vt cosine theta, while y is going to be vt sine theta minus half g squared, gt squared, sorry. Now, we have all these formulas, that's good and all, but to actually implement auto aim, we need to find the angle to launch it, right? So let's look at Wikipedia again, and scroll down, scroll down, scroll down. You'll see angle theta required to hit coordinate xy. That's what we want, right? Now it says to hit a target at range x and altitude y when fired from 0, 0 and with initial speed v, like I said before, the required angle of launch theta are theta equals arctangent of v squared plus or minus the square root of v to the fourth minus g times gx squared plus 2yv squared, all over gx. If you're like me, you'll see that this formula is huge. This is a crazy formula. And you might be thinking, how the heck do we get this formula? If you're not thinking that, just skip ahead to where I explain how to use this formula and how to put it in your game. But if you're interested, now this section is for you, okay? Now, how do we derive this formula? Let's go back to over here. Now, the first thing I'm going to do is set my color real quick. The first thing we'll do is isolate t. Okay, so we're going to isolate t. That means t is going to be, we have to divide both sides by v cosine of theta to isolate t. So that's just going to be x over v cosine of theta, right? Some basic equation manipulation over here. So now that we have t, we could just plug t into this equation over here. Now, this might look a bit ugly, but you'll have y equals v times x over v cosine theta, and then times sine theta still, minus half g, and then we have to substitute again x over v cosine theta again, but then we have to square that. Now that we have this, the next thing we're going to do, obviously we have to simplify. Next thing we do, y is, you see the v's cancel out over here. I'm just going to mark that as red real quick. This cancels out, right? These two cancel out. So now we're going to have y is equal to, I'm just going to move the sine theta up. Y is x sine theta over cosine theta. And then minus, we have this, I'm just going to move g, the half to the denominator and g to the numerator so that it looks better, right? Gx squared over 2 v squared, because we squared the denominator as well, and then cosine squared theta. This still looks pretty intimidating, and you'll see if you know, if you studied some trigonometry before. Let's just set this over here. You see the sine theta over cosine theta, right? Well, what can we simplify this as? Well, sine theta over cosine theta is tangent of theta, right? So that's tangent of theta. But I'm gonna say that this took me a while too. But there's one more thing we could do to this equation, and if you see, it's with something to do with this term. Now, if we go over here and choose another different color because I'm a color person. No. Okay. So now we have this term over here, right? Gx squared over 2v squared cosine squared theta. Now, we could write this as gx squared over 2v squared times 1 over cosine squared theta, right? Now, what we're interested in is this 1 over cosine squared theta. One of the trigonometric identities is 1 over cosine squared theta is 1 plus tangent squared theta. And if you don't know this, the way you get this is, you know that sine squared plus cosine squared is equal to 1, right? So you have sine squared, I'm just going to, hang on, use a different color. So you have sine squared theta plus cosine squared theta, and then still over cosine squared theta, right? And then now you already see, okay, cosine squared theta can cancel out, right? Leaving with 1, and then plus sine squared theta over cosine squared theta, which is tangent squared theta. And that's how you get this formula, right? Anyway, now back on track. We have this times 1 plus tangent squared theta, right? Now we could actually start, simplifying this a bit, Now we have y equals x tangent theta, right? X tangent of theta, and then minus gx squared. I'm just gonna gx squared 1 plus tangent squared theta, right? Now simplifying this more, we have y equals x tangent of theta minus gx squared minus gx squared tangent squared theta. Now, what I'm going to do next is I'm going to, hang on, for room's sake over here, just going to move this over here. I'm going to, next I'm going to just move all the things to one side and set the other side to 0. Like a quadratic, right? We have negative gx squared tangent squared theta minus x tangent theta, and I'll tell you why I'm rewriting it in the order like this later. Minus gx squared minus y equals 0. And oops, I forgot something. Yeah, I forgot something really big. I forgot that it's actually supposed to be gx squared over 2v squared. That's actually my bad, so I'm just gonna just pretend I didn't do that, you know, it's still over 2v squared, okay? So then this should be gx squared tan squared over 2v squared, and this should be gx squared over 2v squared. Alright, so now I'm just going to tell you the reason why I rewrote it like this. Now, if you have a sharp eye or anything, you'll notice something strange. Or, shoot, my bad. Something interesting. You'll notice that this actually forms a quadratic equation, right? And it doesn't look like one, but if I point this out, it'll be really clear. Now, first term, we have this tangent square theta. Second term, we have this tangent of theta. And third term, we don't have any tangent. Isn't that what a quadratic is? Basically, x squared plus bx plus c. Yeah, that's quadratic, right? And also, that's the reason why I moved it all to one side. So I could, you know, start solving for some stuff. Now, before, now we're just going to get back on track. You see we have this over 2v squares that are kind of annoying, right? We're just going to multiply both sides by 2v squared. So that we're going to get negative gx squared tangent squared theta minus, I'm just going to rewrite this as 2xv squared tangent theta minus gx squared minus 2vy equals 0. V squared y. Yes. So, we have this ugly looking thing, and next thing I'm going to do is just make this a bit cleaner by removing some negatives. Because you see we have a lot of negatives. I'm just going to multiply both sides by 1 or negative 1 to clear some stuff out. And yeah, that's going to be a plus 2xv squared tangent theta plus gx squared plus 2yv squared. Alright, let's see. Oh, I did another oopsie. This is supposed to be a plus, right? From I accidentally rewrote it wrongly. Right? We have plus positive x tangent theta, and I accidentally wrote it as negative. You know, I'm not perfect, so yeah, I make a lot of mistakes. So if we have this, or we're just gonna erase it real quick. Yeah, that should be a minus, and that should be a plus, right? So we have this, right? Now we're gonna actually do the fun part. We're actually gonna solve for this quadratic equation. And what we're solving for? We're solving for tangent of theta. Let's say, remember the quadratic formula? Negative b plus or minus the square root of b squared minus 4ac. Now, I'm going to label this quadratic real quick. So, you'll notice gx squared is our a value in this. Negative 2xv squared is our b. And this entire thing is our c value. Now, we can do some fun quadratic stuff. Set it back to black. Now, negative b. What's negative b? That's 2 xv squared. Plus or minus square root. This is going to be a long square root and a bad looking one. But the square root of b squared, what's b squared is basically just going to be 4x squared v to the 4th minus 4a, which is gx squared, and c is gx squared plus 2yv squared. And then that all over RA, which is 2gx squared. Now, I want to, yeah, this is a pretty nasty looking quadratic, right? I'm just going to point something interesting that we can simplify inside here. Now, I'm just going to move to the other side because I'm running out of room, right? Anyway, we rewrite this, right? 4x squared v to the 4th minus 4gx squared, and then times gx squared again, plus 2yv squared. Right? That's our discriminator. Right? So now, there's something you notice. Do you know something? Right. I notice that there's a common GCF. You see it over here? 4x squared, 4x squared. So that means we can actually just factor a bit into, we could factor out 4x squared. And we're left with the v to the 4th minus g times gx squared plus 2yv squared. Right. Remember, we're in a square root. So basically, we could actually move this 4x squared out and turn that into a 2x, right? That's how square roots work. So I'm just gonna rewrite the entire quadratic equation again. We have 2xv squared plus or minus. Remember, the thing we moved out of the square root is square root of 4x squared, 2x. Root. Now we have v to the 4th minus g, and then gx squared plus 2yv squared, then all over 2x squared. Okay, 2gx squared, sorry. Now, another thing you notice, we notice that there's another thing we can actually factor out. You see this over here? This all have a common g factor of 2x. So now we can simplify this, and we're left with v squared plus or minus the square root of v to the 4th minus gx squared plus 2yv squared, and all of that over just just all over gx now. And I don't see anything less that's simplified. So now we can set that equal to our x, right? Which is tangent of theta. Now, we are really close to finding the angle, right? We just apply an arctangent to both sides, and we're left with the final formula. We are left with theta equals the arctangent of v squared plus or minus square root of v to the fourth minus g times gx squared plus 2yv squared, and that, extend the square root a bit, all over gx parentheses. Ooh, that is our angle. And let's just check with Wikipedia, right? Just check to make double sure. Make sure. Theta is arctangent. Yeah, we have that. Of v squared. Do we have that? Yeah, we do. Plus or minus the square root of v to the fourth. We have that. Minus g times gx squared plus 2yv squared, right? And all over gx. Isn't that cool? We, from just these two tiny equations, manage to do all this math, all this math, and finally get this really complicated, but I assure you that it works. This formula that's why I love math so much. You could just do so many stuff. It's really powerful. All right. Now, if you skipped this part, welcome back. And now we're just gonna explain how we actually use this formula. Right. Now, you might be wondering, there are so many variables in this. I have no clue what even to plug in. So I'm just gonna help you with that real quick. And okay, the first thing we want to do is our v. If you saw my explanation before, yeah, you know v is our velocity of the projectile. And now next we have g. G is going to be how much gravity the projectile has, because all projectiles have gravity, right? Next, we have x and y. What is x, y? Now, x, y indicates the target position we want for the projectile, right? We want the projectile to hit this target position sooner or later. So that's how you use this formula, right? Plug in your velocity for the projectile, the gravity, and the target position, and you should be good to go. Now, at school, I made some Desmos graphs, link in the description, that can help you to visualize how you actually do this. Now, the first one we have is a graph that shows you the trajectory of the projectile given the angle. So let's just say our velocity is maybe 5.54, g is 0.71, and let's just change our angle. Okay, if we set this to maybe 53 degrees, random number, you see what trajectory this projectile will have as an angle from 53 degrees. And if I play this animation real quick, you'll see it goes and hits the collision point. And inside here you'll see, oh, we do have the formula here. See over here, v squared plus blah 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 blah. Right? We have the formula that's used to calculate the angle. And if we see over here, we inputted an angle of 53 degrees, and in radian form that's 0.93. But this usage of the formula also gave us 0.93, which means that this formula actually does its job and gives us this angle. Now, that might be a bit hard to explain in this graph, but anyway, I have another graph that will tell you the collision point, the angle given the collision point, which is far more what we want. We want this. We want this in our game. Now, let's just say I have a collision point maybe here. It will say, oh, the angle required is 74 degrees. And if we move over here, 72, 80 degrees, 71, undefined degrees. What does that mean? Now, I forgot to tell you something. Okay, something really cool about this is you see this discriminant over here, v to the fourth minus g times gx squared plus 2yv squared. Now, when it is less than 0, or when the solutions are imaginary, basically, that will indicate that you can't reach this projectile. It's just too far. Like, no matter what the angle is, like maybe 60, 45 degree, maybe no matter what angle you try, you cannot reach that collision point because your maybe velocity is too big, or maybe your gravity is too little, or maybe just target's too far. That's what it means. Now, you see this plus or minus, right? How we got it from the how we got it from the quadratic solving. That basically means we have two different angles we could plug in, right? And I'll go back to the graph. Let's sit it back here. Okay, we have two possible angles. That's what the plus or minus basically means. The first one you see is on the graph over here. In the second graph, if I switch it, it's way shorter, but it also takes way less time. If we say over here, you see the expected time is maybe 89.5. Over here, it's only 35. And here's why there's two possible angles. Okay, I'm just gonna make a new canvas, and here's why. Now, let's say you have nice coordinate system, right? Nice, very good looking coordinate system. Let's say you have this square, okay? This shooter who's gonna shoot at an entity, maybe over here. Now, how do we, what angle do we need to shoot at here? And I said before, there are gonna be two angles we could shoot from. The first one is a very direct path, right? Very direct, takes a little time. But then the second one is a really big arc, and it goes over here. It takes a lot of time and has a bigger angle. Generally, what you want in a game is you want this lesser angle trajectory, so that it hits the target faster, and so the target has less time to run away. So yeah, you should probably use the lesser angle, but you can use the greater angle in some cases. Those are the two types of angles, the two possible angles you could get from the solutions. Now, that's basically how you use the formula, right? But there is something really important that I have to address before we go on to the code. Now, I'm making my game in Pygame, which is a library, written for Python. And the main difference that I needed to address is the coordinate system of Pygame versus the actual Cartesian plane that we've been using the entire time. Firstly, Pygame has a coordinate system that starts on the top left with 0, 0. And by the way, a lot of other libraries also start with 0, 0. So what I'm going to say will apply to some other libraries, like maybe SEO or something. But anyway, as we go to the right, the x will increase. And as we go down, the y will increase. Now, Cartesian system we have over here, it's kind of opposite, right? A bit opposite. It starts at the bottom left, 0, 0, increases x like the Pygame to the right, but the main difference is the y, like as you go down, the y decreases, right? That's different from Pygame. As you go down, y increases in Pygame, right? So for this, we have to kind of basically adjust some stuff. The first thing is, okay, so we have this shooter, right? Let's just say angle over here. Now, in the same fashion, for the Pygame, it'll look like this, right? And I'm going to put some example coordinates over here. Maybe this is maybe 100, 400, and this is 300, maybe 275, okay? So we have this, and we have this. If you notice here, maybe over here, it could be like 100, 175, okay? That is a really bad one, but anyway. You'll see at the Cartesian plane, the target position is greater than the shooter's position, right? That's not the case with the Pygame, right? It says over here 275 and it says 400. It's actually less than the shooter. Why is that? And of course, the reason is the difference between the Cartesian Y system and the Pygame Y system. And for that, this brings me to another important thing. Sorry, I'm getting really off track, but we'll be here soon. Now, we in the Wikipedia, right? Wikipedia says that this formula only applies when fired from 0, 0, right? Well, our positions aren't always fired from 0, 0. In fact, they're probably not fired from 0, 0. So we're going to have to offset some things, right? Let's say we have this target and this shooter. Now, the shooter position isn't 0, 0, right? Obviously, it isn't 0, 0. So how do we, this formula won't work in this case. It won't work. That's really sad, right? But we can make it work by actually setting the position, like offsetting it to 0, 0, and offsetting that position to 0, 0. And then only then, we could actually use the system to, shoot at each other, right? So basically, we have to offset. Now, going back to the original problem we had, let's see. Going back to the original problem, we need to find a way to offset for the Pygame because it's obviously going to be different, right? Now, in the Cartesian system, the way we offset is we subtract the shooter's x position from the target's x position, and then we subtract the shooter's y position from the target's y position, and then that's how we get our offsetted target. So we could use the formula. Now we're gonna have to apply that to Pygame. Now, how do we offset in Pygame? Well, as usual, like the quotation system, we're gonna have to subtract the shooter's x position from the target x position. But what's different is the y position. We're gonna have to offset things a bit differently. In the quotation system, right, you have to subtract the shooter's y position from the target y position. But in Pygame, because the y system is inverted, you're gonna have to subtract the target's y position from the shooter's y position. So it's gonna be, it looks like 400 minus 275, as opposed to maybe 275 minus 400 on the quotation system. And this is really important, the difference between these two, right? One is subtracting the target's position minus the shooter's position, but this is actually the shooter's position minus the target. Now we could actually finally start looking at the code. Now, I have my GitHub repository on my web browser. You could also look at it in the description. And some important files you need to consider are Projectile system, NPC combat system, and this projectile component.py. Now, I'm just going to say my game is written in ECS. If you don't know what that is, that's Entity Component System. It's going to look a bit weird, but you'll get the gist of this, okay? So, now, in this over here, we have a projectile, right? This projectile will be on every single projectile that we have. Every single projectile will have this projectile class, okay? Now, we have a velocity, okay, that's good. We have the entity it's shot by for maybe achievement purposes, you know. And we have some damage. Then we have the angle of the fire. We have the gravity, and we have the time. Now you notice there's going to be two helper functions. You have rho x and rho y, and they both accept a t. If you'll notice, return math.cosine of the initial angle times velocity times t, and then the same for the y. Now, you'll see that this basically implements the formulas we talked about over here, you know. X is vt cosine theta. In here we have x equals vt cosine of theta, and y is vt sine theta minus half gt squared. Yeah, vt sine theta times gravity times t squared over 2. That's the same, right? So, yeah, we have these two helper functions, and we're going to use them soon. But now we have a projectile system. This just, you know, actually moves the projectiles, okay? Now, okay. This says, okay, we're going to iterate over any entity that has projectile position, and graphics. That basically says, hey world, we're just going to iterate over every single projectile, okay? That's basically what it means. We're going to update the time, right? We're going to have we're going to calculate the x position and y position given the time, and we're going to set the position, right? Since we offsetted the thing to 0, 0, right? So we have to add the spawn positions back to the positions. That's what this code does, right? So that it actually could, draw on the appropriate spot in the game. We had a slight problem, but it's fixed now. So anyway, let's go back to our page and and back in the projectile system, we just calculate this basically calculates how much we're going to rotate the graphics by so that it actually looks cohesive and stuff like that. And then that's basically all there is to the projectile system. Of course, there's some like particle spawning, some damage, some some projectile deleters. But anyway, that's basically it for the projectile system. Okay. Now we're on to the thing of how to calculate it. Now, first of all, we're gonna say this line of code basically says, "Hey world, we're gonna iterate over everything that might have an attack." Okay, just basically iterate over every entity basically. And then we're gonna say we have some attacks over here. You see, oh, there's a melee attack, there's a melee weapon attack. We don't need to know about this stuff. That's not part of this video. What we do need to know is starting here. Oh, if this entity has a range attack. If this entity has a range attack, we're going to execute this code, right? And ignore the comments. First of all, we're going to find the target position of the range attack's target. Now, here comes the part where I was talking about, the offsetting. Now, we have this X target and Y target. We set X target to the target position .x minus the shooter's position x. That's the X coordinate, right? And then the Y target is set to the shooter's Y position minus the target. And that's what we said as well, right? Moving on. V is going to be 20. So this basically means our projectile's velocity is going to be 20, and our gravity is going to be 0.6. So it can actually calculate the angle, right? Now we have this. Discriminator is v to the fourth, right? If we go back over here, v to the fourth minus, right? Because we want the lower angle. We want v to the fourth minus g times gx squared plus 2yv squared. That's right. Now, I said before, if the discriminator is less than 0, which means if the solutions are imaginary, that means we can't reach it. And that's what we said over here. If we can't reach the target, then I guess just skip this range attack for now, okay? Just skip this. We can't move on from here, sorry. Just wait another time until you get closer, okay? Now, finally we have over here. We find the angle with the formula we had, which is going to be the arctangent of v squared plus, this range attacks ideal parabola. I haven't discussed this before, so I'm going to open up another window over here. And over here in AI component, we're going to have our range attack. Now, this range attack, this ideal parabola, basically tells us, remember when we have two different angles? We had two possible angles in here, a shorter and a longer. That's what we're doing right now. That's what we're doing. The ideal parabola says which of the two possible angles we want. Now, if we go back to over here, it says, this basically says the ideal parabola is going to be either -1 or going to be +1. And if we look over here, we multiply the ideal parabola by the square root of the discriminant. Right? What this means is this kind of, emulates the plus or minus over here. Remember, over here we have this plus or minus thing. Now, the user or the programmer can set, basically, they can set which type of parabola they want. Maybe they want the one with a higher angle for maybe a rocket. Maybe because a rocket has to, travel a lot before it lands, right? Maybe they want a missile and stuff like that for the ideal parabola, right? So that, yeah, just know ideal parabola times the square root of the discriminator. That basically does a plus or minus. And then we finally divide by gx, like we did in the formula over here, right? You'll notice that I added this thing. If x target is not zero, otherwise math.pi/2. Now, why did I add that? Because what if the entity is like, the target entity is just directly above the shooter? Now, if we have it directly above, that means x is going to be 0, right? The x target is going to be 0. And we're going to basically be dividing by g times 0, which is 0. We can't divide by 0. So then I say, oh, well, if it's 0, the theta is going to be math.pi/2, or 90 degrees, which makes sense. Now, we're just basically done. We're basically done. Yeah. If we have, if the cooldown just passed, if they can fire, then we finally create a projectile. This projectile will have a velocity of v, an angle of negative theta if x is greater than 0, otherwise negative math.pi/theta minus theta. Now I have to open up this over here. Why do I have that? Well, something to do with Pygame again. Now, if you see over here, we have this. Let me just draw maybe over here. Right? We have this angle theta, right? That basically will make a parabola that's over here, right? So think about this. As the parabola increases, the y offset increases as well, right? Like, this is going to be 80. Let's just say this is going to be 80 at the top. Okay? Remember, we add this. We have to add this to our projectiles. And yeah. Unfortunately, we can't do that. Because if we add this to our projectiles, plus 80, wouldn't the y position just decrease, right? Remember, because Pygame is y increases as it goes down, right? So that basically means that the arrow will go down instead of up. That's not what we want, right? So then we have this negative theta. This is going to be negative theta. And that you see over here. You see over here, yeah. Because it's going down, that means it will have a negative y, right? So maybe negative 80 or something, right? That means if we add that, we're basically going to be subtracting 80. And that's what we want. We want it to go up. We want the projectile to go up, not down. So that's what the negative theta is for. That's what the negative theta is for, okay? Now moving on. And by the way, this else minus negative math.pi minus theta, that's just something a bit quirky, with my projectile system. So you might not have to do this, but for me, yeah. Anyway, we set the damage to 1 just for testing, We have the gravity, and we have a shot by entity. And then we finally, unoffset the projectile, right? Over here, we just unoffset it and put it back into the word space. And yeah. And then we have a projectile graphics and stuff at the arrow, And that's basically it. That's basically all there is to, the NPC combat system, And if I run my game over here, you see, if I move more, you see, it starts shooting at me. And it got me. It got me. See? Boom, boom, boom. If I move over here, it still gets me. It still gets me. Boom, boom, boom. Still getting me. It is really accurate, like down to the pixel accurate. So, yeah. That's how my projectile system works. And that's pretty crazy, just like from this all the way to this is insane. That's why I love math and programming, Make big stuff happen, from tiny, you go from small to like super, super big. That's just why I find math and programming so